Another reaction is the oxidation of methyl ketones, means a CH3CO group that indicates methyl ketone. Now here R can be H or alkyl group. Now such ketones can react with the bromine or iodine and sodium hydroxide, that is alkali, to give CHBr3, that is bromoform, or CHI3 or iodoform, respectively. Now consider this molecule, that is acetaldehyde. It contains a CH3CO group. Now iodine first substitutes the methyl group by iodine group, so that each H atom is converted to HI, and one I enters in the position of H. So you get HCOCI3. Now that will react with the NaOH, and liberation of CHI3 and HCOONA, that is sodium formate. Is the product. Now a compound containing CH3CHOH group can also give this reaction, because iodine is a mild oxidizing agent which oxidizes CHOH group to CO group with the removal of 2 H atoms as 2HI, and this can further react with the iodine to produce CI3COCH3, and that will react with the NaOH, producing iodoform and the sodium salt of an acid. For example, here CH3COCH3 reacting with the 3I2, producing CH3COCI3 plus 3HI. Then this CH3COCI3 CH3COCI3 will react with the NaOH, and there is removal of CHI3 and CH3COONA. This is sodium salt of acetic acid, sodium acetate. Now one specific reaction of aldehydes and ketones having at least one alpha hydrogen atom undergo first an addition reaction in presence of dilute NaOH to form a compound called aldol, ALDOL, which on heating eliminates water to form an alpha beta unsaturated aldehyde or ketone, respectively. Now consider acetaldehyde, CH3C double bond OH. Now the functional group here is CHO, and this carbon is alpha carbon. There are 2 hydrogen atoms connected to alpha carbon, so 2 alpha hydrogen atoms. Now here Acetaldehyde splits into, here we have 2 plus 1, that is 3 alpha hydrogen atoms, and acetaldehyde split into HCS2 CHO, and this CO bond polarizes, and H as H positive connects to this oxygen, and the CH2 group as a whole goes to the CH, and we get CH3CH, CH2CHO, and OH. Now CH3CHOH, CHHCHO, we can write it so to eliminate a molecule of water, and we get a double bond between these two carbons. So the product will be CH3CH double bond CHCHO. And on numbering the carbon atoms, here preference is given to aldehyde carbon 1, 2, 3, 4. So it is a but 2 in 1 al enal. So but 2 enal is the product. For acetone, a mild alkali like barium hydroxide is enough to produce aldol reaction, and here in the previous case it is an aldehyde group and alcohol group, and combining the aldehyde group and alcohol group we give the name aldol. Now for acetone, the alpha carbon here has 3 hydrogen atoms connected to it, so 3 alpha hydrogens, and CO group polarizes like this, C plus O negative. Then here this bond will be shifting like this, here also this bond will be shifting like this, and H positive connects to oxygen, and CH2 connects to this carbon, so we get CH3C, CH3, OH, OH, and CH2 connected to this carbon, bond CH2, CO, CH3, and it is called the ketone. Now ketone on heating can eliminate a molecule of water, so HOH removal, CH3C, OH, CH3, CH2, that is written as CH bond H, and COCH3, so that removal of HOH will produce the alpha carbon here and the beta carbon here. With respect to the ketonic group, this is alpha and this is beta, and we get alpha, beta, and saturated ketone. And when numbering the compound, you number in such a way that the ketonic group, which is the main functional group, gets the least possible number 1, 2, 3, 4, 5. So it is 4-methyl pent 3N2-on. Net reaction both examples after reaction with alkali and then heating is a condensation reaction. And here the 2 alpha H atoms of aldehyde combines with the oxygen atom of the carbonyl group, removing a molecule of water, and we get CH3CH double bond CH-CHO, and this is an aldehyde 1, 2, 3, 4, so it is top 2 enal. We have seen it earlier. In the case of ketone also, the alpha carbon here donates 2H for formation of water, so that the carbonyl oxygen combines with the 2 alpha H atoms, removing a molecule of water on heating, and we get this compound. We have named it earlier. Then another example, CH3CH2CHO and CH3CH2CHO. Here the alpha carbon is this one. The 2 H atoms of alpha carbon combine with the oxygen atom, and we get a double bond between the CH and the C. So CH2 double bond CH3CH2 CH double bond. So this product should be written as CH3 CH2 CH double bond C, CH3, CHO. So that is the product. If you number this as 1, 2, 3, 4, 5, it is 2-methyl pent 2-enal. So it is a product. The alpha H atom is acidic due to a tautomeric process. This is alpha carbon, this is alpha H. The CH bond will be shifting like this, and the valency of this carbon increases. To decrease the valency, the CO bond polarizes in this direction. We get C plus and O minus, and when this pair of electron comes here, the positive charge of carbon is neutralized, and H as H positive combines with O to produce OH. So this is keto form, and this is enol form. So the tautomerism is called the ketoenol tautomerism. Now coming to cross-aldol condensation. Cross-aldol condensation occurs between two different aldehydes or two different ketones, or between an aldehyde and a ketone. For example, the reaction between acetaldehyde and acetone. Now here 4 different types of products are possible. One, the reaction product between two acetaldehyde molecules, and then between two acetone molecules, and then between the acetaldehyde and acetone molecule. This reaction can happen in two ways, that is, the alpha hydrogen of ketone combining with the oxygen of acetaldehyde, or the alpha hydrogen of aldehyde combining with the oxygen atom of ketone. So two different products can be formed from the cross-aldol reaction. Now here the first case, the oxygen atom of acetaldehyde combining with the alpha hydrogen of this molecule. So we get CH double bond C, CH3, CHO. Then the alpha hydrogen atom of ketone combining with the oxygen atom of this molecule. So we get CH3, CH2, CH double bond CH, CO, CH3. Now we have taken acetaldehyde and acetone, so the reaction should be written as CH3, CH double bond O, then H2, CH, CO, CH3, 1 NaOH dilute, and 2 heat, removal of water like this. We get CH3, CH double bond CH, CO, CH3, then a second product, that is CH3, CO, CH3, and H2, CH, single bond CH, double bond O, so that water is removed like this. NaOH 1 and 2 heat, CH3, C double bond CH, CH3, CHO, So these two products are the crossed cancer products of crossed aldol products of acetaldehyde and acetone. Now, coming to cancer reaction, I repeated this reaction earlier. There is important reaction. Aldehydes which do not have an alpha H atom undergo self-oxidation reduction on heating with the concentrated alkali. Now, formaldehyde HCHO. So this molecule does not possess an alpha carbon and hence no alpha hydrogen. Two molecules of formaldehyde react in presence of concentrated alkali, potassium hydroxide or sodium hydroxide may be used. Now an aldehyde on oxidation gives an acid, and then an aldehyde on reduction gives an alcohol, a primary alcohol. This may be written as HCH2OH, so that a molecule of water is also getting reacted. So HCOOH, CH3OH. So two molecules of formaldehyde and water gives, in presence of concentrated potassium hydroxide on heating, we get formic acid and methanol. Formic acid is the oxidation product of formaldehyde, and methanol is the reduction product of formaldehyde. So formic acid, FORMIC, formic acid, and methanol. So that is cancer reaction. Then another example where there is an alpha carbon, but there is no alpha hydrogen here, because to this carbon a carbon is directly bonded, so that there is no alpha hydrogen in this case. And two molecules of this compound, and it may be named as 1,2,3. So 2,2-dimethyl propionaldehyde. In presence of concentrated NaOH, the thing is that CSO group is getting reduced to CS2OH and CHO group is oxidized to COH, one molecule of water being incorporated. Actually we get the sodium salt because we are using alkali. Now the corresponding alcohol and the corresponding acid are formed. The CHO group is getting reduced to alcohol CS2OH and it is getting oxidized to COOH. Now coming to the preparation of aromatic aldehydes, and the most common one is benzaldehyde, and benzaldehyde is a resonance hybrid. We get the ortho and para positions with positive charge, so that electrophilic substitution of benzaldehyde will give the meta product preferentially, because meta position does not carry any positive charge. So relative to ortho and para positions, we say the meta position is electron rich, and here aldehyde group exerts minus M and minus I effect. So we say the aldehyde group is meta-directing in electrophilic substitution reaction. Now coming to the preparation of benzaldehyde, now one reaction used is a named reaction called the Etart's reaction, that is toluene is oxidized using chromyl chloride, CHROM by L, CHLORID, CrO2, Cl2 is chromyl chloride, Now this chromate chloride ionizes as Cr positive and O negative. Then 1H as H positive is getting connected here, so that CH negative is getting connected to chromium. Then two such H atoms are removed by reaction with the two molecules of chromate chloride. So we get CH bonded to chromium, then OH by polarization of this O as O negative and combining with the H here, so OH and OH here. Then there are two Cl atoms, and such a compound is formed which undergoes hydrolysis, chemical reaction with water, addition of H and OH here, so that CH is combining with the two OH groups. We get CHOH twice, which eliminates a molecule of water like this, and the next product to HCr OHCl2, and this molecule eliminates a molecule of water, producing CHO, that is benzaldehyde, and that is attached reaction. Now oxidation using chromium trioxide in acetic anhydride, the temperature used is 273 to 283 Kelvin. Now CrO3 is the oxidizing agent. We get a diester CHOCOCH3 OCOCH3, because this acetic anhydride contains two CH3CO parts. Now oxygen atom is supplied by chromium trioxide, so OCOCH3 group is connected to the CH3 group by replacement of 1H, and then another OCOCH3 group, oxygen being supplied by CrO3, is getting connected to the same carbon by replacement of 1H, so that we get a diacetate, which on hydrolysis gives OH twice, so that HOH addition occurs here. So CH3COOH is removed, and we get CHOH. Then this CHOH molecule being unstable removes a molecule of water, and we get CHO. So that is one method using chromium trioxide in acetic anhydride. Then another method, that is side chain halogenation followed by hydrolysis. We use chlorine in presence of UV light. H nu indicates a photon, PHOTON, photon energy packet. Then chlorine molecule dissociates, and then chlorine radical combining with the CH3 produces CHCl and HCl. Then another chlorine radical combining with this CH2Cl producing CHCl2 and HCl, so that it is a free radical reaction. Then CHCl2 undergoes hydrolysis. You neglect this benzene ring. Then this CHCl2 acting as an alkyl halide. Two chlorine atoms replaced by two OH groups in water. Then, as usual, eliminates a molecule of water to give benzaldehyde. So these are the methods of preparation of benzaldehyde. That's enough. Next, coming to the reactions that you will see in the next video. Thank you.